STA 3532 Introduction to Statistical Quality Control, Chapter 2 Methods and Philosophy of Statistical Quality Control. This is also Chapter 1 Introductory lesson. So we are step by step moving to the lesson 3 and 4. So lesson 3 and 4 is the core of this course. So we are getting the background knowledge for that two lessons in those lessons. I think you can understand this lesson by reading also. Anyhow, I am going to brief the important facts only. If you need to take the clear understanding about those things, you have to read the lecture note again. So this is methods and philosophy of the statistical process control. So statistical process control is a collection of tools that when used together can result in process stability and variability reduction. So it means that here statistical process control, that is variability reduction. So variability reduction means if we reduce the variable, it means quality is improving. So variable reduction means quality is improving. So we are doing the statistical process control to improve the quality. That reduction variability means, as an example, if you are taking a factory or an industry, suppose you are making packets of sugar. So if you need to produce 100-gram packets, but it is actually that if you measure, all the packets are not 100 grams. It can be vary in small amounts, sometimes 98 grams, 102 grams, so on and so forth. But in that statistical process control, so you have to reduce the variability. So reduce the variability means that improving the quality. There are some tools to check out this quality. So then so they are there, then it is mentioned here there are 7 major tools. There are 7 major tools of checking the process. So they are histograms, stem and leaf diagram, check sheet and Pareto chart, cause and effect diagrams, defect concentration diagram, scatter diagram and control charts. The most important thing is the control charts. Then we are going to learn about the control charts in chapter 3 and 4. Then chance and assignable causes of quality variation. A process that is operating with only chance causes variable present is said to be in statistical control. Then chance of causes variable means that they are, then if only chance of causes variables are present, then it means that is in statistical in control. But in here also there are some amount of natural variability can exist. So here some amount of natural variability can be existed. Natural variability, but can be exist, but comparatively that is very small. So that is very small amount. Right. So then if it is only causes of variance, chance causes of variable present, that it means the process is statistical in control. And a process that is operating with the presence of the assignable causes is to be out of control. So then assignable causes mean there is a variability. Variability may be present in the output of a process, right? So variability is an output of a process. variability may be present in output of a process. And also then this can be happen in three ways. This can be happen in three ways. Sometimes that it can be happening that's improperly adjusted machines and improperly adjusted machines. That if you have machines in industry, if it is improperly adjusted, then assignable causes can be happen. Adjusted or control machines, then it can be out of control machines. Or then sometimes there are some operators, then operator errors can be happen, operator errors, as well as sometimes that when we use some raw materials for a industry, then defective, if there are defective raw materials, then assignable causes can be happen, then process going to be out of control. Then it means defective raw materials can be also there. So then the process is out of control. And the eventual goal is of statistical process control is reduction or elimination of variability in the process by identification by the assignable causes. So then goal of the statistical process control is, so we have to identify the assignable causes. First thing is we have to identify the assignable causes, then we have to reduce these assignable causes, or we have to eliminate these assignable causes in order to improve in the quality. That is the core of the statistical process control. Then statistical basis of the control chart. This is also an introduction. We are going to talk about what is control chart, and we are doing the calculations related to the control charts in next two chapters. However, that control chart is the effective tool in the reducing variability in the statistical process control, right? Then so we can write that control chart is an effective control chart is an effective tool in reducing variability much as possible. So we are using control charts to reduce in the variability. So this is a control chart. The control chart means here so you can see in the x-axis that sample number of time, and the y-axis sample quality characteristic, sample number or time. So for the x-axis we are using sample number or time, and for the y-axis sample of quality characteristics is used. So then control chart means, then so here we can write that control chart means that graphical display, that is a graphical display of a quality characteristic. So here you can see the quality characteristics now. So that is a graphical display of a quality characteristic has been measured or computed from a sample versus the sample number of time. So here quality characteristics versus the sample number time. This is a meaning of a control chart, right? So then we can write the control chart is a graphical representation of a quality characteristic has been measured or computed from a sample versus the sample number or time. Sample number time. So that is the meaning of a control chart. So then here you can see that statistical basis of a control chart. So the statistical the control chart contains a center line that represents the average value of quality characteristic corresponding to the in control state, right? So the control chart is containing a center line. This is the center line, that is the center line. This is the center line, and the control charts contain a center line that represent the average value of a quality characteristics corresponding to the in control states. So most of the plots that it is closer to the center line. So if you observe this control chart, you can see that most of the plots are closer to the center line. That's close to the center line, and there is only causes of only chance of causes are present. So here only chance of causes are present. So if it is assignable causes, what happen? So that is goes to out of control. So if only the chance causes are present, that is in control. So two other horizontal lines called upper control control limit, upper control limit, that is UCL, and the lower control limit, LCL. So if the process is in the statistical in control, so all the plots here, this is upper control limit, then this is lower control limits, then all the data points are in between these two. It means this is a control chart with statistically in control. If one or more points go beyond these two limits, it means that is out of control. So here also sometimes so here, yeah, that's out of control situations. So you can see here at least one of these one if at least one of the points beyond the control limits, if the process is out of control, then here you can see this point and this point is go beyond the here upper, it is go beyond the upper control limit, and this one is go beyond the lower control limit. Then it means at least one point go beyond the point, that means that is in our process is in out of control. So here you can see that this process is in out of control because this is go beyond the control limits. And also if points behave in systematic or non-random manner, then the process could be out of control. Then here you can see all the data points are in between the upper control limit and lower control limit. No, this one is go beyond there, only this one, but all the others are in that case also that is out of control. But here also you can see suppose this point also in that in between lower control limit and upper control limit, but here you can see the pattern is not random here. That is there is some systematic behavior in here. If it is in systematic behavior, it means that is also not a statistical in control process. So if there are in between the upper control limit and lower control limit also, it can be out of control, because if the data points behave systematic or non-random manner, it could be out of control. Next one, relationship between hypothesis testing and control charts. There is a close connection between control charts and hypothesis testing. So the connection is, so in the hypothesis testing we are taking the critical value, so then here also we are taking the critical values that is same as the that are the control limits, upper control limits and lower control limits. So we are consider as the control limits critical value in a hypothesis testing. That is means it has a close relationship between these two. So then relationship between hypothesis testing and control charts. So we can take an example here. We have a process that we assume the true process mean is mu equal 74. So here given mu equals 74, and the process standard deviation, that is sigma, equals 0.01. that is given a population, that population mean is mu is 74 and population standard deviation is 0.05. And sample size of 5 are taken, giving a standard deviation of sample average as x, but then out of this population we draw a sample of size of 5. So then sample average is given, it means sample mean is given as x bar, so then x bar is also equal, you know that in earlier courses we learned in statistics, if that sample population mean is closely equal to the sample mean also always, so then we can write x bar is also 74, but so population standard deviation can be varied. Then here standard deviation of the sample average we can find using this equation, that is process standard deviation sigma divided by square root of the sample size. So here now so we need to find the sigma x by using this equation, that is sigma over root n. So sigma x we can find sigma, the value of sigma is given, that is 0.01 divided by root 10 sample size, that here given n equals 5, then it means root 5. So we can find the value of sigma x, then that is 0.01 divided by 5 square root 5, so that is 0.01 division 5 square root, then answer is what happened. So you can take 0.01 divide by square root of 5, then answer is it can become 0.00447. The answer is 0.0047. That is the value of sigma x then, right? So that is the value of sigma x. So you can use this equation sigma x bar equals sigma over root 10 to find the standard deviation of the sample average. So then control limits can be set at standard deviation from the mean. This result in 3 sigma control limits. Sometimes that is not always, that is no need to be a 3 sigma control limits, but normally we are taking in between the 3 sigma unit, that is choosing the control limits is equivalent to the setting up the critical region for the to the testing hypothesis. As an example, so that is if you take here sigma h naught, that is a null hypothesis h naught, that is mu here, that is equal 74, no? And also we can take that alternative hypothesis also, then mu not equal 74. Then this is that control, taking the control limits is equals to the hypothesis testing in that is critical region in the hypothesis testing, right? So as an example, so here that set the 3 sigma unit, no, then we can calculate the upper control limit equals mu plus 3 sigma, so mu is we knew that value of mu, that is 74, sigma x 3 that is 0.00447, not 47, that is 447, that is the value now 0.447. yes, so we can write 3 sigma x bar. So then value is 74 plus 3 times 0.00447. so we can find the value of upper control limit, then 74 plus 3 multiplied by 74 plus 3 multiplied by 0.00447, then answer is 74.01341. so we can write 74.01341. this is the upper control limit. Then we can find the lower control limit, that is also 3 sigma units, that means mu subtraction 3 sigma x bar. So mu is 74 subtraction 3 times sigma x bar 0.00447, then we can find the value. Now we can find 74 subtraction 3 multiplied by 0.00447, it's come 73.98659. then the answer is 73.98659. these are the upper control limit and lower control limit. Then the equation is to find the control limits, that is control limits for upper and it means mu plus or minus 3 sigma x bar. This is the equation we have to use to find the control limits, both upper and lower control limits. And here you can see the graph, and for this one, that mu equals 74. This is the population. This is about the population. Mu is 74 and standard deviation is 0.001. that is the population. This one is the population. And this is draw out the sample here. This is the sample. We taken sample of 5. No, that is given in the question. We taken sample of 5 here, and then we found mu is equal to the this one. Then sigma x bars we found at the value 0.00447, and also we found the upper control limit 74.01341 and lower control limit 98.659. so you can see that most of the that is a normal curve, no, that is just like normal curve. So you can see that most of the points that is center line, most of the points is closer to the center line. So then here all the data points are in between upper control limit and lower control limit. It means this process is statistically in control process. Then types of control charts. There are two types of control charts, that is attribute control charts and variable control charts. We discussed those things in lesson 1 also. Then attribute control charts we are using for the discrete data. We are using these for the discrete data, it means counts. And variable control chart we are using for the continuous data. Continuous data means the measurements. These two types we talk about in next two lessons. So we have to do calculations belong to these control charts also in the chapter 3 and 4. And types of variability, right? There are 3 types of variability. So first one is the stationary behavior, uncorrelated data, and second type is stationary behavior, autocorrelated data, and the third one is non-stationary behavior. So these 3 types of process variability can be seen in the processes. So here that if it is uncorrelated data, then here there are no correlation can be seen, no correlation of data points, no correlation in the first one. So you can see that that is go here and there is no relationship between the data points. And here that is a stationary, that is not changed with the time then. So you, when you are learning that time series analysis in the last semester, you can see that this types of uncorrelated data we called as white noise. This is somewhat similar to white noise in time series analysis. Time series you can this is you can learn in time series, right? And if we so if there is no uncorrelated data no, so there is no pattern. So in here that past values in it means that values, if we can observe those values and we can't predict the future values, so it means the past values of the data are no help in the predicting the future values. In here past values not helping the, we can't predict, no, we can do the predictions we can't do the based on the, in this type we can't do the predictions based on the fast values. So then this one is the this process is a statistical in control process, this one in control. So these things we can see in the stationary auto uncorrelated data. Then this one also stationary, it means sorry, this is not changed with the time, but that is autocorrelated data. So here also if autocorrelated means there are no correlation between these data points, but so there is a correlation between the other terms. So here these also data points, it means observations are dependent, observations are dependent. Observations are dependent, there are no relation among the data. So that is also a stationary, it means not depend on the time, previous one also not depend on the time, and this is in control, that is also in control process, statistically in control process. But here you look at that, there is an unstationary behavior. So you can see that here and here also there you can see that another thing, if you learn if you draw a line in here, look at here. So most of the data points are in one side, no, it means we can see another things that means has a tendency to move in moderated runs in the either side. So if it belongs to one side, so that characteristics also can be seen in the second diagram. Then here non-stationary behavior, there are changes, there are so many changes, there are changes, and this is not stationary one, it means that is depend on time, that is dependent on, that is out of control. Then that out of control, this one is the out of control state. And here also then most of the times we can see these types of processes in the chemical industries. Then we are going to talk about the Sheward control charts. That is the most effective when in control process data are stationary and uncorrelated. Then the Sheward control charts are effective in that's detecting out of control conditions. So we have they are effective then they are effective in detecting out of control conditions, conditions. Right. So and so most of the our discussions in next chapters of the control charts, that's actually in chapter 3 and 3 we assume that that's in control data are stationary and uncorrelated. So we are assuming these things stationary and uncorrelated, and we are going to do the calculations. Then popularity of the control charts. Control charts are proven technique for the improving the productivity. So it means it means that successful control charts, here we are talking about this one, control charts are proven technology for the improving the productivity. So in a successful control chart, it means that reduce the scrap and rework. It means if we reduce the scrap and rework, it means that is increase the productivity and production capacity, right? And also if it means there are no scrap and rework, it means that reduce the cost also. That's why that these types of control charts popular in the productions. Then second one is control charts are effective in defect prevention. So it means if we have the effective process control, there are no non-conforming products. So it means control charts are effective in the defect prevention. The third one is control charts prevent unnecessary process adjustments. So if the control charts are there, so we know that upper control limit and lower control limits, as well as there are some limits also we are discussing in the next few time. So then here that the control charts prevent the unnecessary process adjustment. It means can identify the background noise and abnormal variations. If we have the control charts, we can identify those things, then we can prevent the that unnecessary actions in that process. So we can increase the performance if we can identify those background noises and abnormal behaviors, right? As an example, so suppose a factory a garment factory or something. So if we can see there is a fault, so it is happen frequently. So if we can identify those things, so we can prevent this process adjustment. Then fourth one is control charts provide the diagnostic information. It means it allows the implementation of a change in the process that improves its performance. So fifth one is control charts provide information about process capability. That means control charts provide information about the important process parameters and their stability over time. So then this allows to estimate the process capability. That's why these control charts are more popular because of those reasons. And this is the general model. We talk about this earlier also, but that is not the general model. That 3 sigma units, that is the general model. So it means center line we are called that's mu w. It means mean of the sample statistics w, and upper control limit mu w plus L times sigma w, and the lower control limit is the mu w minus L sigma w, where L is the distance of the control limit from the center line, and sigma w is the standard deviation of the statistics. Earlier we talked about L equal 3 1. If we L equals 3, that is mu w plus 3 sigma w. So then here we have to talk about some errors. So there are two types of errors. One is the type 1 error, that is we called alpha error, and also the type 2 error, that is beta error. So you talk these in the statistical inferences also. And then type 1 error means the manufacturer risks. So in the factory when we are doing a production, so sometimes maybe have the faults, right? So it means faults means that's go beyond the data one or more data points, one or more data points go beyond control limits, right? If one or more data points go beyond the control limit, it means there is a error. So if that manufacturer can identify this error, so there is a false alarm. So if that false alarm can be found, then they can correct this error, right? So that's why I call that is manufacturer risk. So type 2 error means that beta error, that is consumer's risk. It means if they in a manufacturers produce the products for the shops and shops, but they didn't know about there is a fault. So that's they didn't know about. Then manufacturers that consumer has to get these false goods. So then that is the manufacturing. It means that the data points in between data points in between control limits, because that's why that false alarms can't be identified in between control limits, but that is out of control, then this can be identified by the consumers, out of control. Then if type 1 error is increased, it means type 1 error increase means the manufacturer can identify the false items. Then type 2 error is decreased, because that is corrected. If the type 2 error is increased, then it means it means that good is not good enough. And the 3 sigma limits. The use of 3 sigma limits generally gives a good results in practice, right? If distribution of quality characteristics is reasonably well approximated by the normal distribution, then 3 sigma limit is applicable. So 3 sigma units is approximable for the quality characteristics in normal distribution. That should be normally distributed, and these limits are often referred as the action limits. So for the 3 sigma units we call action limits. And there is another type, they are 2 sigma units, 2 sigma limits. So for 2 sigma limits we call the warning limits. Warning limits, if used, are typically at the 2 standard deviation, that is 2 sigma. That is 2 sigma limits, 2 standard deviations. One or more points fall between warning limits and the control limits, so closer to warning limits, process may not be operating properly. It means, so 1 or 2, that means there is a process here 2 sigma and here 3 sigma. This is warning, this is the warning limits, and this one the action limits. So 1 or more points fall between the warning limits and the control limits, the process limits, or the close to the warning limits. Here close to the warning limits, the data points lie in there. Then what happened? The process may not operating properly. It means there can be a false. So you have to find this false in the false if it is lie closer to the warning limits. Then here there is a good thing and bad thing in the warning limits also. That good thing is the warning. The good thing is warning limits often increase the sensitivity of the control chart. It means sensitivity is the control chart is increased by the warning limits. It means that if that goes to beyond the 3 sigma, it means action limit, its process is going to the out of control. But if the warning limits are there before going to the out of control, we know that is going to be out of control, so we can do necessary actions to process keep as in control. And the bad thing is warning limits could result in the increased risk of false alarms. So it means that it's go near to the 2 sigma, then it means always you can see the false alarms. And the next one is the average run length. The average run lengths that give the number of samples that should plot in control before outside the control limits. It means then as an example, if told that if we produce something in a in a factory, so there are suppose there are 200 good things that produced, and after 200 there is a false item. So then in that case, that average run length means before that false item there are 200 goods produced. So it means that average run length is equals to 300. So we will discuss through that examples also. Then here the average run length is very important way determine the appropriate sample size and sampling frequently. So you can find that average run length 1 over p. P is equals to the probability that point exceeds the control limits. So there is an example. Consider a problem with control limit set of 3 standard deviation from the mean. The probability that point plots beyond the control limits, again that is p equals here given p equals 0.0027. so you know that to find the average run length. Average run length equals 1 over p. It means 1 over 0.0027. so you can find ARL as, so we can find the ARL as 1 over 0.0027, 370.37. it means that is closer to 370. The meaning of this is after 370 that goes to out of control. That is the meaning of this. And finally, a process is considered out of control if any of these following occur. So process is going to be out of control out of any of these going to be may occur in a process. One point of plots outside 3 sigma control limits. At least one is goes outside for the 3 sigma control limit. It means that process is in out of control. Second one is 2 out of 3 consecutive points plot beyond the 2 sigma warning limits. It means if there are 3 consecutive points near points, then at least out of 3 consecutive points, at least 2 go beyond the 2 sigma warning limits. It means that is also out of control. And 4 out of 5 consecutive points plot distance of 1 sigma or beyond from the center line. So 4 out of 5 sigma limit it be between the 1 sigma limit go beyond, then that is also in out of control. Then fourth one is 8 consecutive points plot one side of the center line. If means if lies one side of the consecutive 8 points one side of the center line, it means that is also in out of control. That is a brief introduction about control charts. So then now we are knowing something about what is a control chart, what is a statistical process control, so how we are going to control this in an industry. So now you have somewhat background knowledge about the statistical quality control. So now we can do how we can going to do the process control, so we can solve the problems related to the industries, and also in the how we can find they are in the statistically in control process or out control process. So in the next two chapters we are going to deal with the problems. It means we are going to solve the problems related to the control charts. So we will meet next time in the next video with the do the calculations related to the control limits. Thank you.